You don't want that to drop down. I mean, the relativity can be confusing. So if you kind of panicked and messed that up, maybe that can sort of, that's understandable. And after this, it's going to be a little more straightforward, not purely weird and confusing. But indeed, you should take this as an indication of where you stand. I thought on the whole, most people did pretty well, but not. There was not everybody. Let me see. I have a couple of comments about the exam, about what people did. Let me erase all this. Oh, there was a couple of silly things, and most of you did this right, and in fact, there's not a wrong, but it makes me wonder what happened on the homework, or maybe the people who did this aren't in class often. Hello? That's the use of light year and year. If you get a distance in light years and the speed of light in terms of c, a light year divided by c is 1 year of time. And a couple of people tried to go into meters per second. And clearly nothing wrong with it, but it's a morass. You don't want to have to do that. Also, a couple of people literally took rules, I guess you guys learned in high school. I remember I had them drummed into me when I was in high school about significant digits. If I write 0.7c, I don't mean do the whole problem with one digit. In general, significant digits means don't write down everything that's on your calculator. If it's an exam, just use common sense. A few times in your life, or if you become a professional scientist like I am, then you're going to worry a lot when you finally publish a paper about how many significant digits they are. But it's not going to be as simple as, well, what was the smallest number of digits that I was given? Right? I mean, those rules you learned are kind of, I don't know. I mean, they're kind of cartoonish, frankly. So just use common sense. Don't write a bunch of digits, but don't round unnecessarily. Okay, those are trivial things. There's a serious thing, on the first problem especially, but all the way throughout. Some of you did very well. Many of you got the right answer. Many of you did not get the right answer and did not set up the coordinate system, right? And you've got to do this. And when you do your homework, you've got to do this. Don't ever skip it, even if you can do the problem. I never work a problem of this style, and I've been doing physics for more than 20 years now. When I work your homework, when I sit down to think about it, I never skip the step of drawing a diagram. I never skip the step of labeling the diagram. Even when I can do a problem like that, which isn't always, your problems aren't that easy. So, if you've got Anna and you've got Bob and they're doing their thing, okay, you draw it. And actually, since, the drawing was there, you could label the drawing I provided. Better yet, redraw it and draw it with a coordinate system, and label your times and your x's like I did. When I do this at the board, I'm showing you how to do it. Don't see what I do and think, oh, okay, that's cool, but he did all this extra stuff. I'll write it down in one line. I took off points much more if you got the wrong answer and you did not set it up well than if you got completely the wrong answer, but you set it up well, okay? I mean, if you went at the problem completely wrong, but you drew a nice drawing, you got more points, okay? And I'm going to continue to do that, and it's going to happen throughout your physics career. Part of you learning to do physics, it's not freeform. I mean, if you're going to go build a building with bricks, you don't get just to decide, oh, I'll put them sideways, or I'll do this, or I'll do that. There's a technique. The bricks are square for a reason, and you're going to lay them down, and they're going to stack up. And part of what you're learning here, and I'm showing you, and you're going to learn in recitations, and this applies to all your physics classes, is what is the technique to solve problems. And a lot of you are skipping a lot of steps in just the work you're doing. And that's the reason you're not going to get the right answer. It takes more time, and it takes more effort. But it actually takes less brain power, okay? Conventions on how to do things are important. Einstein joked there's this thing, it's a complete side note, but if I have, you know this symbol, which actually we're going to use today, suppose I wanted to calculate your average grade. Each of you has a score, SI. That was the score, and for student number N. If I wanted to calculate the average score, I add up the score for each person, and that's a way to talk about it, right? That just simply means S1 plus S2 plus S3, where these are all your scores. Blah, 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 blah. And the average I divide by the total number. Okay? In certain, especially in relativity, he did this for relativity. In relativity, often you want to do something where you want to sum the score maybe times the weighting. Okay? So for each score, I'm going to give you a different weight. I'm not really going to do that, but suppose I wanted to, everybody whose name starts with an S, I'm going to give them 5 more points. I'm going to weight their grade more important when I average this up. But anyway, so when I simply do Sn, this basically means S1 times W1, that's some other number, like that. Okay? Einstein decided that instead of writing the sum symbol, he would make the convention that if I write Sn Wn, and n is here and n is here, it's implied that the summation symbol is there. And it's called the repeated index, because that's an index, that little subscript. It's called the Einstein repeated index summation convention. And he once joked that that was his biggest contribution. Okay? Supposedly, because I didn't hear it. Why am I telling you this? The point is the way to work problems matters. Don't skip steps. We're trying to show you how to work problems. Work it the way I work it, okay? You'll develop slightly your own technique. That's fine. I'm not talking about that. If you develop a technique that I can tell you've got a technique, that's great. For a lot of you, though, you don't even have a technique, and you're not going to develop one unless you systematically try, okay? So, do that, right? Don't skip steps, write a drawing, label. I haven't finished here, right? I want to label it 1, label it 2. And also, if you're not in practice, if you're not doing it every time, then it gets real confusing. Where do I put the 1s, where do I put the 2s? And you've seen me do it, but it's not the same as doing it yourself, okay? Okay, so enough moralizing, but some level is good for you. Gotta say it. Also, in the first problem, many of you switched frames where this is S prime and this is S. You can do that, but then you only could get the right answer if you took V to be negative. And you don't have to do that. I would urge you never to do that, because it's just confusing and you have to think hard. But, sort of your choice. Okay. Any comments or questions? Yeah. Yeah. I just got the exam graded. I'll do the solutions as soon as I can. I actually gave today I'm doing the experiment. I gave a colloquium yesterday at Johns Hopkins, and I got up at 5. So I'm doing the experiment, which is a product of 1 over sleep times caffeine is a constant. And we're going to see how it goes. Yeah, I know, I'm a geek. All right. All right, so I wanted to start off by talking about, let's see if I can find some white chalk. Oh, wow, cool. All right. The white chalk is colored yellow on the outside. Very confusing. I stopped by talking about collapse of wave functions, and let me just talk about it one other way. I've mentioned that people have actually done the experiment of shooting electrons at a double slit, right? And they saw an interference pattern. So sorry, let me erase the electrons for a second. Suppose this was classical light waves, electromagnetic waves, and they propagate out. and they form a double slit interference pattern. There's nothing magical about that. It's kind of neat, it's kind of cool, but you think of the wave as getting here. Remember the way you derive it is you say when a wave hits a small hole that's small compared to a wavelength that sort of circularly radiates, that's Huygens principle. And you can just see it with water waves. If this was water, you would think there's absolutely nothing weird here, right? And if it's electromagnetic wave, fine, okay? But so then the weird thing is if we replace the wave by electrons, by God on a screen, what we see is they come in and they're on average, they're following a pattern, which again is the interference pattern. Okay? Now we're not going to calculate this exact quantum mechanical thing, but if I were, it's actually, if you've calculated fully how the waves form this pattern, you've done the quantum mechanical thing. We're just going to take a plane wave e to the ikx that minus omega t that we spent Wednesday and Monday just, fussing over, okay? And we're going to apply the same exact idea as we did for the E&M wave, and we're going to get this. So let's look again here. What's going on between matter and wave? There is a wave function. It's associated with the particle in some way that is just simply not intuitive. We don't live at the subatomic scale. Essentially, we're big compared to h bar in some units. Take some measure of us, and it's big compared to h bar. So I don't know what it means that the particle has a wave-type property, but I do know what it does. What it does is, however that wave is associated with the particle, that wave went through these two slits. One electron, in a sense, does this, right? Classically, one electron can't get in the center, yet that's the maximum of this pattern. Didn't draw it quite right, okay? So one electron comes along, and there is a wave function, and it goes through two slits, and it forms this pattern on the other side. Or at least mathematically, we can say that that's what happened. Then the electron actually smacked the screen, okay? That counts as an observation. Remember I told you that if you observe, did I say this? That if you observe a system, you change it, right? It smacks the screen, that counts as an observation. Because I don't even like that language of observation, but it's very common to talk about this. I mean, it interacts with another thing is the way I like to think of it. It interacts with the screen, and then that localizes the electron. The momentum is completely lost at that point, so you don't violate the uncertainty principle. And it does end up as one of these dots. Say, if I did this right, that one. And it's right there in the center. And it couldn't have gotten there classically. And you tell me what it did in between. I don't know, but that's quantum mechanics. But I mentioned collapse of the wave function. The collapse of the wave function is the notion that just before it actually hit the screen, somehow the electron was represented by this probability distribution, which I can calculate even for one electron. I can think of it as being a wave that went through both slits, formed this pattern, which in principle goes off to infinity, although the peaks, with vanishingly small peaks. And then it hit the screen, and that wave function collapsed, and boom, the particle was one place. And the collapse was not limited by the speed of light or something like that. It just did. Okay? And that's this. I think it's a little more explicit here what I mean by the collapse of a wave function. Okay? Somehow when the electron hits here, the wave function way over there knows, give it up. I had some probability. It was one part in 1,000 if I was way down there at the floor, but I had a probability. Gone. It's the way it's collapsed, and the guy's up there. Okay. So today I need to spend a little more time giving you a sort of background, and then hopefully we can move on to the first the first real problem after just a plane wave. But a little more background. I want to talk a little bit more about the Heisenberg uncertainty principle. All right. So delta P, delta X is greater than h bar over 2. First, let me make a side comment. I justified this, I motivated this by looking at waves that I got, e to the ikx, that's a plane wave, and I added it with different k's, and I saw that it formed packets in x. It was key, this mathematical construction, e to the ikx. Or if you don't like that, you know, cosine kx, sine kx, so to get the same qualitative behavior. We also had, though, that the full wave had e to the ikx minus omega t. Omega and t similarly are multiplied together inside of this exponential, or inside of a cosine or a sine. Okay? And so there's a similar relationship. Now here, k and x, well, h bar k times x is p times x. H bar omega is E, remember, energy. So there's a similar relationship between energy and time. So those are the two Heisenberg uncertainty relationships. This one's even, you know, in a way weirder, I think, than delta P, delta X having an uncertainty. We certainly believe in energy conservation. But at the subatomic world, on a short time basis, I can have energy not conserved. And so, in fact, there's a view of what we call the vacuum, which is that at any instant in space, I can spontaneously have, well, what really does happen on a practical level is like I'll have matter, antimatter spontaneously generated, say an electron and an anti-electron. And that, there's an energy cost, m electron c squared, plus a tiny bit of kinetic energy associated with that, two of those, because I'm creating an electron and an anti-electron. They have the same mass. They live for they live for a time that's short. Well, it's given by that. Or let me just put an approximation there. So I borrow a little bit of energy from nothing, and then for a short amount of time, that's okay, as long as I don't violate this relationship. And then they disappear again, the two annihilate away again. Okay? And I know that sounds kind of wacky, but that actually is our view, that is going on all along. Just sort of, you know, in the vacuum. I know that sounds wacky, but that is the modern view. And it actually has tangible effects, which I'll try to mention right at the end of the semester. So there are these two uncertainty relationships. Okay. We're often going to just deal with that one, but this one comes up too. Now let me say something about what I mean by delta P and delta X. And actually what this little bit I did to introduce the Einstein summation repeated index, well, people don't call it the Einstein, although this is, they call it the repeated index summation convention. The little thing I did to introduce that sort of applies. Let's think about an example of scores. Suppose I had 5 student scores, or 5, let's say quiz scores, S1 or homework scores. What did I pick? 3, 5, 8, 6, 3. 3, 5, 8, 6, 3. So this is familiar to you. Suppose those are the scores on some quizzes. What's the average? The average, you may not be so used to writing it this way. Here I'll use the S sub I. I is 1, 2, 3, 4, 5. I mean, clearly I just mean add up those numbers, divide by n. 8, 16, 16, and 6, 22, and 3 is 25. There's 5 scores. The answer is 5. All right? That's fine. Now, whoever did this didn't get 5 5s. They got a bunch of different grades. So there's some delta S associated with that. Okay? Right? There's kind of a range of what they got. Maybe some other student got an average of 5, and it's because they got 3 5s and 1 4 and 1 6. They clearly had a much smaller delta S than this student, right? So let's think of a mathematical way to represent it. The first thing you might think of is that, well, okay, let me take each score and look at the difference from that score and the average score. Okay, that's a simple thing to do. And so let's average again. Oh, by the way, are you familiar with that? If I write a bar over something, that means average it. I hope that's not confusing, right? You can also just say, it's often also written that way. That means average. I'm just going to use a bar usually. Okay. So I'll write the difference between one score and the average, and then I'll sum that and divide by n, and that's an average difference, if you will. Okay? Well, the problem with that is that quite clearly I could have scores, let's say the central score was 5, and then I had a 2 and a 2, and that's 3 lower, and I had an 8 and an 8. So that'll give an average score of 5. Both of these are 3 below, both of those are 3 above, and if you plug in here, you're going to be adding -3, 0, 3, and 3, and that sums to 0. So this thing will end up being 0. That's no good. I mean, it's the same number as if someone got 5 5s. Okay? Right? Graphically, suppose there were a lot of grades, and I'm kind of writing the number of grades with some value s. If I have a distribution which is symmetric, then this could be the average, but this would have 0 of this quantity because there's as many above as below. Now this may not be a crazy thing. Suppose I had a distribution which looked like that. The average might be somewhere down there, and this thing would not be 0. Still, because it's 0 so easily, we don't use that. Next thing you might think is, oh, okay, let's take the absolute value. That's pretty well behaved, right? So for this student's scores, I would have said this is 3 and 3, 0, 3 and 3. So I would have had 4 3s, which is 12, 1 0. So I'd have 12 fifths. In this case, it'd be 12 fifths. And that's a pretty good, which is what? 2 and 2 fifths, 2.4. Yeah, that's a pretty good representation, okay? Yeah, but it's a little ugly because I'm taking the absolute value. That's kind of not fun. So we don't do that, right? So you've probably seen this, but here we go. What we do is we define what's called the standard deviation, sigma, which is the standard deviation. Deviation. It's a measure of deviancy. It's more or less exactly that, but instead of taking absolute value, which is kind of an awkward mathematical construct, another way of making something that might be negative positive is just to square it. Okay? So I'll write the sigma squared down. What I mean by it is take the score, subtract the average score, square that, and take the average of that whole thing. Okay? If I want sigma alone, I need to take the square root of this whole monstrosity. Okay? Here I wrote out what averaging means, right? But this is exactly the same thing. Well, it's not triple equals. That is the same thing, though, is if I write s minus s average squared average, right? This is just that, but I didn't put the I down. I just wrote the bar, and that allows me to not write the I, the sum, and the 1 over n, okay? But I didn't mean anything. It's a shorthand, but I don't mean anything different from that. Now, there's one nice little tweak about this. Let me square that out. All under the average, which again, remember, the average bar is a shorthand for actually performing this operation, all right? It's very convenient, just write S bar. Averaged it. Well, you haven't averaged it yet. You got to go do it. But I can just write it down that way. okay? But let me square it out. I mean s squared minus 2ss bar plus s bar squared, right? So right, this is just s sub I. I'm going to square it and then average that, etc. Okay, but let's think about this a second. So this is s squared average. These things just add up, so they separate out. If I had them in a summation, I can just separate the terms. This is 2s, and I'm going to average it. This number here is a constant. It is the average, and so when the averaging doesn't affect it. If I have something I'm averaging, and there's a constant inside, that can come outside the summation symbol. It's just a factor for all the terms in the summation. So that doesn't get affected by the averaging. So this is 2s average plus s average squared. Average that, but again, this is already just one number, and the average of it is the same thing. So this is s average squared again, right? And so this is minus 2s average squared plus s average squared. So finally, this is s squared average minus s average squared. Okay? How many of you have seen this before? Oh, quite a few. It's important, so maybe we keep beating you with it and, showing it to you. But it's really common. But I wanted to go through this because this is what when I just tell you that delta p and delta x are related, that's kind of imprecise, except I give an actual mathematical inequality here. And this is what I'm going to mean if I really want to go calculate this. I'm going to mean apply this procedure. Here I did it with discrete counting, but I could do it to a wave function as well, okay? Replacing a summation with an integral, and it's the same sort of notion, okay? So just to sum up, sigma squared is s squared average minus s average squared, which you can just write down, but that's not how you started. You actually started from this definition and you got to there. All right? And so when I say delta p delta x, I really kind of mean that. Okay? And I'll do that for by distributions and momentum or whatever. The probability that I calculate from the wave functions. Now, often we an important situation that arises often, and again, I think most of you may have heard of or studied like last year, is when you have a probability. Let's talk about the probability of a score having the following shape. There's some typical score, S0, and it has this famous bell-shaped curve. All right? Mathematically, there's some normalization out front. And it has that form, and this is called a Gaussian. You guys did get this last year, right? Not everybody? How many have not seen this? Okay, good number. Well, let me talk about it a little bit slowly. There's a constant out front. The constant out front just normalizes it so the total area under the curve is 1. Okay? If you actually figure out how to do this integrate that over minus infinity to infinity, you'll find that the integral of this part just equals that. The sigma comes out, maybe not surprisingly. Look at this business end. Exponential in something. It's the distance from the average value. This is the average value. I call it S0, but in fact that also is the average. If you average this thing, you'll find that the central value is the average, okay? Call it S0. So it's the difference from S0, you square that and you divide by some normalization. Again, so what, and also this whole notion of a probability distribution, you may or may not have seen this. Even if you've seen it, I bet you haven't, there's a good chance you haven't fully digested it. I think I was midway through grad school before I finally really figured out what you're doing here, all right? I write this down, that's very simple. It's this thing. It's called the probability distribution. It's like, say, the probability that a score happened, okay? It just mathematically does do like this, right? So if S is S0, this is e to the 0. So it's got some max, it's big. Well, it's e to the 0. Any S that's not S0, this is some term, and it's e to the minus that. So it's like 1 over e to that, so it's getting bigger and bigger and bigger, so it falls off on either side, right? That's mathematically the way it works. Now there's another notion. Could this represent your grades from this exam? And I don't mean in a practical sense, like did your grades look like that? I mean in a mathematical sense. Could this represent the grades from your exam? The answer is they can't. I mean, it depends how we want to talk, but there's a mathematical sense in which no, you cannot. Can you imagine what that would be? Where just that is not like the grades in your exam. It's continuous. You had discrete grades. What is the probability that we had? If this is a probability distribution, the probability of actually attaining the value S0 is what based on this? Do you know? The peak here is 1 over root 2 pi sigma. That's just a mathematical thing for this constant to give the overall integral 0. Is the probability 1 over 2 pi root sigma? The peaked value? I said this is the probability of the thing, and that's the value of it if I read it off. If you tell me what sigma is in real numbers, I can calculate this number. The answer is no. The probability is 0, right? Because I have, well, let me explain when it's not 0, and then maybe it'll make sense that it could be 0. If instead of asking the probability of one thing being true, if instead I ask the probability, this is some S1, and then this is some width ds. The probability of S between S1 and S1 ds is equal to probability at S1 times ds. And then that's a finite number, right? If this whole integral is 1, if the whole area is 1, and I pick off some chunk here that's about, say 10% of the width, and it's down by a factor of 3, that might be about 3% of the total, okay? It would be a number 0.03 when I did that, when I calculate that, okay? And you have to talk about that. This is called the probability density. And then you have to multiply it by some amount of, some range to talk about the actual probability. This is a little bit off the topic from quantum mechanics, but it's worth seeing and it's worth understanding. Because Gaussians are going to come back. And in that sense, if I ask the probability of one actual number, it's shrinking ds to 0. And then it's the probability is 0. Here's where it comes in. Suppose instead of the way I assigned you grades, I gave you grades. I always rounded. Well, I didn't grade to a half point, which I could have done. So effectively, I rounded to the integers. So we didn't have a continuous number. You had grades which fell in bins. There's some number of you that got that, and some number of you got that. Maybe no one got that, etc. And so then I can ask. I can maybe graph it this way, but I could ask, what's the probability of someone getting a 65? We count up the number of people that got 65. We divide by the total number of grades. That would be the probability that someone got 65. If instead I looked at your exam and I had not just a lot of precision, infinite precision. So each one of you had a unique number between 0 and 75. And I mean an infinitely unique number. I get, as an irrational number, right? It just was, I gave you a 71.8 blah, 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 off to infinity. And then you said, well, what's the probability that a person got 75 plus, 0.1 blah, 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 which is slightly different than what I just said? The answer is 0, right? So if I make it a continuous distribution, I can't talk about the probability at a point. I have to talk about the probability within a range. And if you try to ever calculate anything, if you don't have that concept in mind, it'll lead to madness. Okay. We'll file that away. Oh, also, sorry, I have to, since some of you hadn't seen a Gaussian before, so sigma sits here as just this kind of normalization number in the numerator, in the denominator. But in fact, there's this, if I calculated sigma for this beast, and how would I do that? I said before that sigma squared was I square it and I average it minus the average squared. And when these were just discrete numbers, we knew what that meant. If they're not discrete numbers, here's what S average means. And this is important for quantum mechanics, okay? And I'll do it, I'm going to come back to it, and you're going to see it again. It's going to be in homework, it's going to be in exams, but let's just do it now with this probability distribution. The average of a probability, the average of a value, if P of S is the probability of that value, is to take the probability distribution, P of S, multiply it by S, and integrate over all S. Actually, since we're not punitive and we don't give you negative grades, the integral goes from 0 to infinity. Or maybe it goes from 0 to 75 on this exam, okay? Whatever the range is. Or not that punitive. Right, so that's the meaning of S average. The 1 over n you thought of before already got taken into account by having this prefactor here, right? You have to have that P of S ds all by itself integrates to 1. That's to find the constant, and then you find the average this way. The average of S squared is to do that. That's what it means to find the average of something, the something being a function, S, a variable, if you will, score. Or in quantum mechanics, it's going to be an energy, or a momentum, or a position. I might find, I've been saying that the wave function is going to give me P of x and t. Or in a lot of cases, we're going to deal with it's just P of x. Then if I ask, what's the average of x? It's going to be the integral of a probability distribution. Now that came from psi star x psi. It's going to be that, x dx. Okay? That's what we're going to do with probability densities. Okay? So is that clear? So now, if I actually want this in this situation, that is to say P of S times S squared minus S average. Well, actually, I'll probably calculate it this way. I'll first do this. And then I'm going to have to subtract off. And then I'm going to have to subtract off. That's this term. And then I'll subtract off P of S times S ds. That's S average. And then I got to square it. That is the meaning of sigma squared for continuous distribution. And that's what I'd have to do. And I won't prove it, but if mathematically I've made that the P of S, then indeed this sigma, which is just, I wrote it as a constant in this formula, is in fact that. Okay? It's a feature of a Gaussian distribution. Right? Is this too abstract for you? You understand what I'm saying? You're actually going to do these integrals, right? Okay? You're going to do them soon. So you'll get an idea what it means to do that integral. All right? The other thing about the sigma is that, so basically, let me erase this little bit of markup on the curve. So if I have a curve like this, and again, this is, let me line it up better. This is S0. This would be S0 plus sigma, and this would be S0 minus sigma. And 68 point. .3% of the integral is inside S sub 0 plus or minus ds, sigma s. Okay? So I've gone slower than I wanted today, so I'll finish with this since it's topical. When you see a poll for the election and they have a margin of error, it's not exactly a nice mathematically well-defined situation like this at all. But it turns out so many physical phenomena do have fluctuations which are given by a Gaussian distribution. They actually use a special form of a Gaussian which applies when you count something. If I go count, if I measure something 1,000 times and the answer is it's there or it's not there, and there's sort of fluctuations in that counting, it turns out there's a prescription which says that if I measure n things, sigma is the square root of n. Sigma squared is in fact just n, believe it or not. And they use that when they give you the margin of error. If they count 1,000 people and they say there's 3% error, if they say the poll had 3% error, where it came from is they're saying 3% is sigma over the number they measured. So it's the square root of n, which is a result, which I won't prove, that is a form of a Gaussian that applies when I count things. And I divide by n, that's 1 over root n. I invite you to plug into your calculator 1 over the square root of 1,000. You will find that is 0.03. And that is the margin of error they quote. And that's exactly where it comes from. All right? And so when they say margin of error, there's a thing that always annoys me in the reporting. They'll say, well, if there's if it's 46, 48%, they'll say, and if margin of error is 3, they'll say, oh, it's a tie. That's a weird way of talking about it. What you mean was, your best estimate is that the guy that had 48% was 2 points ahead of the guy that had 46%. You also know that 68% of the time that statement is true. And 31.7% of the time, that statement was false. It does not mean that it's a tie. It simply means that the difference was within the probability 68% being right. You can take a more stringent thing. You can go out what's called 2 sigma, where there's only about 5% left over, not inside. And then you would double the margin of error. And that's not at all obvious in what they report. If you take that margin of error and double it, the probability that it's wrong shrinks from 30% to 5%, etc. Okay? And so all of the statistics of polling is based on this Gaussian. And we're going to start using that to talk about the probability that an electron is someplace when you come back. I will.